So we've got our final exam tomorrow. This is a fully a review class. I do have some questions that people asked, and you're welcome to ask other questions as we go here. I've tried to summarize the general format for tomorrow here. It's going to be just like test 2 in that I'll send out individual Google Meet requests. I'll do that probably tomorrow morning. And then I'll probably send out the exam right at 11 and we'll just work through it together. I did try to make it more manageable. Now, I learned from the last test, I feel like on test 2, maybe I made it, I don't know if it was too long, but in the format that we're in where it's kind of weird, maybe it was too long. So I tried to make this one slightly shorter, actually, even though it's the final exam and it should be longer than test 2. I tried to make it's actually 1 page shorter. And, you'll have your reference sheet, your cheat sheet, so to speak. So I'm hoping that it takes you less time, right? You should be sort of less sitting there thinking about things because you have got the cheat sheet. And so you should be able to just work through the problems. That's my hope, at least. You can take as much time as you want. We're going to do it during class time. You don't need a calculator. I'm going to ask that you not use one again because I'm testing you on some trig things. And so just, with your cheat sheet, you should be able to write down the unit circle if you really want it and bring that in. Speaking of which, so, it was asked in the chat here, what's the deal with the reference material from test 2? If you want to use that reference material, I'll just say, just put that on your cheat sheet. So the formulas, the unit circle stuff, if you want to bring that stuff in, just put it on your sheet. And so you can use just a full standard computer paper, 8.5 by 11 piece of paper. If you want to write in the back, that's fine. In other words, you can have lots of stuff with you. You just need to take the time to prepare that. Oops. So I think that's all I wanted to say sort of about the general format. Are there questions at all? You're going to do the same thing where, you scan it with your phone and you send it back to me. And I'm going to ask that it's the exact same number of pages as the test, just like I did last time. So that'll help me grade it. So, the sort of the setup and the procedure is going to be just the same as last time. I'm hoping, though, that it will take less time, actually, because you'll have your notes. And it's technically a little bit shorter, actually, the final is. Can I clarify any sort of general questions about the final before we look at a little bit of review?
I have one, Dr. Levy. Well, we submit our test, but
I posted lots of topics and practice problems and things like that to Blackboard too. I know it says that right here, and I've been saying that for a long time. But in the event that someone hasn't started studying yet, shudder. I'll just say that one more time. There's lots of good review material. I would really focus on the material that I posted because that's, I wrote those problems and that's the kind of stuff that I find important, And so I think that's a good idea to really focus on. All right, I'm just going to sort of stop talking for a second and see if anyone wants to ask a question about the test, like format-wise or anything like that. Or if anyone wants to type a question, I'm just going to stop talking for a second and let you do that.
I had one, Dr. Levy, if you can hear me. Oh, dear.
No, you don't have to scan your reference sheet. So the question was, do you have to scan your reference sheet with the exam? Let me think about that for a second, actually. Yeah, and let's not worry about scanning the reference sheet because it's very important to me. I'll say again that the number of pages that you scan should be exactly the same number of pages that the test has. And so if someone used like 1 or 2 pages, front and back of the reference sheet, then it might mess up that length. And so let's just not worry about scanning the reference sheet. Let's just scan the work. And let me just mention that again. Almost everyone did that correctly, but like 2 or 3 people had like 20-page things that they scanned. The way that I'm grading this is I enter it into that website that I returned it to you on test 2, that is, and it looks for the exact same number of pages and it pulls the questions from each page where it thinks the questions are. So if it thinks that it's a 7-page test and you scan 10 pages, the computer gets confused and then I have to go in and manually say like, this is question 1, this is question 2. It's not the end of the world if like 1 or 2 people did it, but the fewer people that did it, the better, really. And it makes you looking at the answers when I return it easier too. So anyway, I just want to mention that again. I saw the exam has 7 pages of questions. Any other sort of formatting type things like that before we get into some review? So someone sent me some homework questions, which I'm happy to go over. But what I would just recommend you not forget about is the review that's posted to Blackboard. And so I'm just going to show you that just in case you're not sure what that is. I'm sharing my screen now, and I'm showing you Blackboard, and I'm showing you where I just want to make sure you can see this right. Yes, I'm presenting. So if you've got my thing pinned, you should unpin because I'm presenting my screen. If you go to course documents and you go down to test topics, practice problems, and solutions here, final exam topics and review problems is a really nice thing to study. So all the topics are right here, obviously, and then the review problems are right here, and then the solutions are right below that. If you haven't done anything else, you should definitely be working through these problems, right? These are like the kind of problems I think are important, for example. And the test will look sort of kind of like these kind of problems. And so, working through these and then again, the solutions are right here, I think is a really good way to study if you haven't done anything else yet. There's certainly lots of other things to do. There's all the homework we've done is also good to do, but that's, those things that I wrote that I just showed you, I think is the primary thing you should definitely know how to do. Okay, any other questions before we do this? I had some homework questions and we can look at those. So the first homework question I had was this one. Feel free to just drop questions in the text, or you're welcome to turn your mic on if you want. This says I'm still presenting. Is that true? No, I'm not presenting, right? Okay. So I had a couple domain and range questions in the via email, which is great. And so I'll remind you the thing we think about for domain. These are both domain specifically. So for domain, and I like asking these questions on tests, you need to avoid dividing by 0, right? So that's one thing you need to do. And the other thing we need to do is we need to avoid taking the square root of a negative, right? Those are the two things that we think about when we think about domain of these rational functions. And so in these two examples here, they're both fractions, and so this one and this one. And so in these two examples, we're definitely going to have to worry about dividing by 0 because we've got fractions. And the second problem has got a square root, and so we'll have to avoid square rooting a negative in that second problem. But in both cases, we're thinking about these two things, right? And so on this first problem, we need to think about dividing by 0, and so let's go ahead and factor the bottom. And so we can pull an x out of the bottom, and it would look like that, right? And so I just factored from here to here. And I wanted to factor because I'm trying to figure out when does the bottom equal 0, right? If the bottom ends up being 0, we're going to divide by 0, and we need to avoid that. And so to avoid dividing by 0, we need that denominator to not be 0. And so this is just a nice, easy equation to solve, right? We factored it, and so it made it easy. And so you set each factor equal to 0 separately. So x can't be 0, and x plus 4 can't be 0, which means that x can't be -4, right? And so these are the two numbers we need to avoid in this problem. We need to avoid 0 or -4. If I plug in either one of those numbers into the bottom, we're going to divide by 0, and that's not okay. And so when we write down the interval, we write down every single number except those two things. So let me just stop there and see if there are questions about those two numbers. We haven't finished this problem yet, but are there questions about how we got there so far? So let's see what this looks like. Let's skip over 0 and -4. So here's -infinity. I'm going to skip over -4. And then I'm going to skip over 0. And so it's everything except for those two numbers. And so if we need everything except for those two numbers, there's 3 pieces there. And so my 3 pieces are minus infinity to minus 4. Don't include it. Minus 4 to 0, right? That's that middle piece that people often forget. Don't forget the piece right between minus 4 and 0. And then the third piece would be the piece past 0, so 0 to infinity, right? And we put unions between them because that means we're going to include all those numbers in all those pieces. Thoughts about that one? You know, one particular person asked these questions, but anyone's welcome to chime in and clarify something. Okay, so in the second one, it's a very similar problem because it's also a fraction, but we also have a square root, and so we need to avoid both dividing by 0 and taking the square root of a negative, right? And so let's do those 2 things in pieces. So let's do the dividing by 0 part first. So to avoid dividing by 0, we need the denominator, so square root of 19x plus 5, to not be 0, right? So we do the same thing as we did in the last problem. We take the denominator and we set it equal to 0, and we try to figure out when that happens, and we avoid those numbers, right? And so here, if we want this not to be 0, we would start by squaring both sides to get rid of the square root, I mean. We get 19x plus 5 can't be 0. And then we would subtract 5 divided by 19, and so x can't be minus 5 over 19, right? And so we need to avoid that one particular point, minus 5 over 19. Well, we also have a square root, and so we need that to not be negative as well. And so that's the second part of this one. We need to avoid square rooting a negative, and so we need that thing inside the square root, 19x plus 5, to not be negative, right? So you set it greater than or equal to 0. That's another way to say not negative. And then this is now just an inequality equation that we know how to solve, right? Subtract the 5, divide by 19, and so x has to be bigger than or equal to minus 5 over 19. And so we put those 2 things together to write down our final answer. Let me pause there and see if there are questions about how we got there, and then we'll write our answer down right here. And everyone's able to see, okay, there's no focus issues today or anything.
I can see just fine.
Okay, so we put these 2 things together, right? So we need to be greater than or equal to negative 5 over 19, but not equal to it from this side, right? So in other words, this not equals part gets rid of the equal here. So when we put the 2 together, this looks like bigger than minus 5 over 19, but not including it, right? I've got an open circle there because this one sort of got rid of the equal sign here. And so that interval would be minus 5 over 19, comma, infinity. Both get parentheses because we're not including either one, right? You always put a parenthesis around infinity. And that's how we think about that. It's good review of domain and range. Thoughts about either one of those or other sort of domain or range type questions on your mind? I am going to try for some long pauses here. I don't know if people are typing. I want to make sure you get your questions answered, so I'm going to do some long pauses. You know, the other question I had from this person was about solving trig equations, which I'm happy to look at. But I was sort of thinking if there were other like non-trig questions that people wanted to look at, maybe we could do all the trig together and all the non-trig. So were there other non-trig questions that people wanted to look at, either domain and range like these, or really anything else, anything from the review, homework problems, notes, anything on your mind, anything non-trig related that you want to look at. Anything from the last homework sets that were due, you know, whatever. Oh, while you're thinking about that, also, I updated the homework grade on Blackboard. So I went in, I downloaded all your homework grades, and I dropped your 4 lowest grades. So believe it or not, you guys completed 37 homework sets this semester. Congratulations, that's amazing, 37. So I usually drop the lowest 10%, and so I rounded it up to 40 and dropped the lowest 4. So your homework average on Blackboard says final web work average. That's final, and it includes dropping your lowest four grades. So I forgot to mention that, sorry. Okay, I'm going to stop talking now. Questions about non-trig things? Non-trig questions, anything?
Does logs count as trigs?
Okay, do people have trig questions? Maybe I'd like to just mention too that I haven't said this in a while, but you know, I have a policy that I'm looking for students to pass the final exam to pass the course. I really think anyone here can pass the final. I know you all can, especially with a page of notes. Anyone can pass the final. But I just want to remind you that that is a policy, and so just encourage you to actually take this seriously. Maybe ask some questions if you have them. Yes, my computer was muted. I'm sorry about that. Have people been talking? Sorry about that. I think I just opened it up. Sometimes my speakers don't work though. Let me just double check that. Okay, I think my speakers are currently working. Sorry about that. If anyone was talking, I saw that Sean asked a question here. Let's see here. Courtney, were you talking as well? I can talk about logs, Sean, sure. But Courtney, did you say something? Still not hearing anyone talking. I don't know if anyone is or not. Sean, what kind of log stuff did you want to talk about?
Can you hear me?
Yes, I can hear you. Yep.
I don't know. I know it's just a good review of it. Just a general review, because I know logs not my, and I said many times, logs not my, you know what I mean.
Sure, I can do a quick summary thing there. So logs go hand in hand with exponentials because they are each other's inverse, and we use logs and inverses to solve log and inverse equations, right? So you use logs to solve inverse equations and inverses to solve log equations, right? And so just kind of quickly, we know that exponentials do this and logs do this. So you can visually see their inverses of each other. Because if you flipped this one around, it would look like that. These ones have asymptotes down here at y equals 0, and these ones have asymptotes right here at x equals 0. And so because they're inverses of each other, they have this relationship that if you have something that says a to the x equals y, you can change that into the log form, log base a of x equals y. I'm sorry, this is not quite the way that it's written. Sorry, this should be a y and that should be an x. And so if you have, in other words, if you have a log equation, this is a question I ask very often on finals, is here's a log equation, rewrite it as, or sorry, here's an exponential equation, rewrite it as a log equation, or here's a log equation, rewrite it as an exponential. And you need to do that sometimes to solve log equations, right? So to solve log of ax equals y, you change it to a to the y equals x, right? And so that's how you relate like logs and exponentials to solve log equations. And if you want to solve a to the y equals x, you would take the log base a of both sides. Because when you do that, you get this. You do like...
You push the paper up, I don't think, I know I can't see it.
There you go. So when you log base a both sides, these things cancel, and then the y just like comes right down. And so that's my kind of like quick and dirty review of how they're related to each other and their graphs, because like questions I usually ask, and you'll see these questions in the review, right? I ask questions like graph a log, graph an exponential, and so you kind of need to know their shapes and where the dotted lines are. I often ask switching between these two things, right? And I will definitely ask you to solve some equations. And so I'm trying to sort of do a general summary of those kind of things. And there are examples of each one of those kind of things in the review. And in the homework. But again, if you just focus, if you do nothing else, you should definitely focus on the review, because again, I wrote those problems and the exam looks very similar to the review. So I don't know if that satisfies you or not, Sean. I'm happy to keep going or ask like a more specific question if you had something more specific on your mind, if that's the kind of thing you were looking for.
I'll go with that. Thank you. There's so much I could ask, but I don't want. I know there's other. You know.
Well, like what? What are you thinking about? Like solving a specific equation? There's also like combining logs, right? There's the log properties.
Log prop. Yeah, you can do. As I said, logs is not my. I could. I'm sorry. I'll shut up. I'm just yakking.
Okay, well, let me know if there is something you want to look at. I know maybe you're having a hard time articulating it, but I'm happy to do that. Can I answer another question for someone else about logs? Someone else want to say something about logs or exponentials? Again, Courtney, I don't know. Were you trying to talk before and I didn't hear you? You're muted, Courtney. I don't know if you are talking about. Anyway, you are. I think I'm ready to listen. Okay. There aren't other exponential or trig, exponential or log equations. I had these questions about solving trig equations, which is kind of the culmination of trig, right? Because you need to know everything that we did. Basically, you need to know everything about the unit circle, about how to find, how to use box number one, like find the x and the y values for sine and cosine, for example, and sort of backtrack. So these are sort of the harder type of trig questions, I'd say. And so I guess what I'm trying to say, if there are more basic kind of trig questions that people were thinking about, it might be good to look at those before this so that this makes more sense. But I don't know if there are. It doesn't seem like people are really interested in asking questions this morning, which is fine. But I am going to pause for a second and see if there are more basic trig questions before we look at solving trig equations. Okay, well, let's look at solving trig equations. So the whole goal of solving trig equations is you want something that says, and sure, we can do it in trig identity as well. Maybe while I'm talking about this, if you wanted to look at, so I posted, in addition to there's some trig identities in the review that I posted, but I also, if you remember, I posted an entire document full of trig identities for test 2. And so maybe, Gabe, if you're interested in looking at a trig identity or two, if you wouldn't mind picking one out that looks good to do from something. Anyway, for trig equations, before we look at trig identities, let's do equations, because that's pretty different. Our goal here was you want something that says, in this case, either sine or cosine. It's usually going to be sine or cosine. We want something that says sine or cosine of our value equals some value on the unit circle. That's always the goal. And the problems that this person sent in are sort of the more challenging type of problems, which is fine. But even the more challenging problems, the goal is to change it into something that looks like this. Because then we know x's and y's on the unit circle, right? Sine and cosine. And so that makes it very easy to kind of solve these things. So that's always the goal. So on this first one, for example, I'm going to rewrite it right here. It says cosine of x times sine. Oops, there shouldn't be a parenthesis there. It should be just multiplication. It's cosine times sine minus 2 cosine equals 0. All right, so our goal is to get sort of sine or cosine by itself and then set it equal to something on the unit circle. And so we should factor out a cosine. All right, there's a cosine right here and there's a cosine right there. And so let's factor out a cosine and get something that looks like this. And so the whole point of doing that, just like in that last problem we just did a minute ago, is when you have something factored, it makes it nice to set it equal to 0 separately. So you do cosine equals 0 and sine minus 2 equals 0. So we're looking for places that sine equals 2 or where cosine equals 0. Right, and so we reached our goal. We got something that said sine or cosine equals some values on the unit circle. That was what we were going for, and that's what we have. At least in this one, right? We'll be able to do this one for sure. This one, we're not going to get any solution from, because where are y values 2 on the unit circle? Well, the y values, the biggest they get is 1. And so this, we don't actually get, we get no solution from that piece. No solution. But on this one, we do get solutions, right? So when we solve these equations, we're thinking about where are the x values 0 on the unit circle. And we're looking at the x values because it's a cosine problem, right? Cosine are the x values. And so we're thinking, well, if this is the unit circle, where's cosine going to be 0, right? Where are the x values 0?
No. And
Yep. Where's the other one?
3 pi over 2?
3 pi over 2, yeah. So the y-axis spots, right? So it could be pi over 2 or 3 pi over 2. Those are the two places where the x value is 0, right? This is like 0 minus 1, and this one is 0 positive 1. But anyway, in both cases, the x value is 0. And so we want to be at one of those two places, and those two places are exactly opposite each other on the unit circle. In other words, if I walked between those 2 points, it'd be a distance of pi. And so that's why we're able to write the answer as pi over 2. So the answer here is x equals, let me start there. Right, the thing that's inside cosine is an x, so it says x equals pi over 2 plus pi k. Because pi over 2 puts us on the first circle, and then when we add multiples of pi, that's what pi k means, it bounces us back and forth between those 2 points because they're directly opposite each other. And so we're able to represent both answers with just one solution by putting pi k on this particular one.
Is it equivalent to say, instead of pi over 2, say 3 pi over 2 plus pi k?
Yep, sure, that would be fine too. Yep, you could put 3 pi over 2 as well. So that would be like starting here and then bouncing back and forth, but it still would account for both those things. Yep, that would be fine.
Now the trig questions where it talks about so like the domain of cosine, tangent, and sine. So like what I mean is that like on the unit circle, so cosine is from -1 to 1, like the value has to fall within there, and sine and tangent on the y-axis it'll fall between 1 and -1.
Yep.
And like what questions are those? Because I was getting hung up when I was solving these.
Are you talking about? I think maybe you're referring to the inverses, trig inverses, maybe.
Probably, yeah.
Let me just remind you that I think what in those problems, those are like this kind of question, like what's cosine inverse of like √2/2 equals what? And on those problems in the notes for cosine, you wanted to be on the upper half of the unit circle.
Correct, yeah, that's what I'm talking about.
0 and pi.
So you look for a pi over 4 value.
Right, so you'd be looking for a pi over 4 value between 0 and pi with a positive one, and so that would be this one right here. It'd be pi over 4.
Correct.
Now, that was specifically for web work. I'm a little bit more lenient and things like that. So I'm not, in other words, if you don't do it right on the top of the unit circle, like if you put this one right here, I would be okay with everything.
Okay.
You don't have to really worry too much about the interval on this. What's important to me is you know like what the question's asking, and that you know how the question works, how it relates to the unit circle, that kind of stuff.
Okay, cool, awesome, thank you.
We can look at this one too. This is the other one that was asked prior to class, the solving trig equations 1. And it's secant of 4x minus 2 equals 0. This one, I remember doing this one previously in class. This is definitely the hardest question in the homework set. I think I'm going to just, I'm going to do a slightly different question. I'm not going to ask one this hard, but I might ask one that looks like this. So instead of doing this problem, let's do cosine of 4x. Let's do 2 cosine of 4x minus 1 equals 0. This is kind of a similar problem, more in the ballpark of the type of question I might ask on the final. Okay, so again, we want it's something to say like sine or cosine equals value on the unit circle. So get cosine by itself, in other words. So add the 1, we'd have 2 cosine 4x equals 1. Divide by 2, cosine of 4x equals 1/2. Bam, we have cosine equals number on the unit circle. And so now we're thinking, where is cosine 1/2? So we want this to be an x value, and we want the x value to be 1/2. And so that happens at pi over 3 spots, right? So it could be pi over 3, or it could be 5 pi over 3. Those are the two places that have x values of 1/2. And so, but notice they're not directly across from each other, right? So unlike the last one where these were directly across, these are not directly across from each other, right? Directly across from this one would be down here, and directly across from this one would be over here. And so this is one we have to write them down separately, in other words, right? And so we want to do, based on this information, we want x to be pi over 3 plus 2 pi k, right? So we have to include the 2 now because we're going all the way around the unit circle, or 5 pi over 3 plus 2 pi k. Again, with the 2. Now, this one's the sort of the added wrinkle in this one is this added 4, right? So this would be the answer if this was just an x inside the cosine. But it's not an x inside the cosine, it's a 4x, right? There's a 4 in there instead. And so we don't want x to equal that. We want 4x to equal that, right? So we want what's inside cosine to be that. And what's inside cosine in this case is 4x. And so it just adds one more step where we need to divide x by itself. Right, so we just divide everything by 4. And then we would have our answer for x. And another page here. It would look something like this. So after we divide by 4, the 4 ends up going into the denominator and multiplying those. It'll multiply the 3. So x is going to be pi over 12 plus 2 pi k over 4. And you could reduce that if you wanted to a 2. That's fine. Or not. Whatever. I really don't care. And it would be 5 pi over 12 plus 2 pi k over 4. What's important is just it's not a compound fraction. I'm not going to fuss over reducing fractions. Someone asked me that in an email, I think, too. Like, if I don't reduce this fraction, am I going to lose points? I'm not going to fuss over reducing fractions on this test. Or any test for that matter, really. Thoughts about that one? Other questions about anything at all? Oh, Gabe asked to do a trig one. Gabe, did you look at trig identities? Did you pick one out? Or do you want me to see if I can snag one? Number 8 and 16 in the identities worksheet. Okay. So let me open that up quick. So again, as a reminder, under test topics and solutions, I posted a very long trig identities practice problem. And it has solutions with it too. So yeah, we can do 8 and 16. Those do just kind of quickly looking at them look like they might be trickier, kind of the trickier variety, but maybe that's a good thing. Maybe that's why we should look at them. So I'm just going to write them down. I don't know if you can see this, but let me just write it down first, and then I'll make sure you can see it. All right, so number 8 says this. Starting to get dark out here. It's starting to rain almost. Almost raining out. Maybe it is raining. Can't really tell. So again, this is from the trig identities worksheet. This is problem number 8. So it wants us to prove that this tangent squared plus 1 equals sine squared, right? So you want to start with the more complicated side and transform it into the less complicated side. And just like on test 2, I'm going to put trig identities on the final, but I'm going to give you options again. So I'll say, like, pick one of the following 2 to do or something like that. And you want to show your work to get partial credit. People did pretty well on these on the last test, though. So let's start with the left side, right? I think the left side is definitely the more complicated side. So the idea is we want to start with this side, do a bunch of identities and simplifications and things like that, and then eventually the last thing we write down, right down here somewhere, it's going to equal sine squared. Right, so we're going to take this, do a bunch of algebra and stuff, and the last thing is going to be sine squared, and that's going to prove that this is true. Right, we're going to start with one side and transform it into the other side. So let's see here. Sorry, I got to adjust my screen real quick. So the first thing we should do is change tangent into sines and cosines. And so I know that tangent equals sine divided by cosine. And so if I have tangent squared, you just square sine and cosine. Right, so the first thing we can do then is take tangent squared and write it as sine squared over cosine squared divided by sine squared over cosine squared plus 1. right? And that's always a good first step, is change everything into sines and cosines. And then you just want to do some algebra, right? You just do algebra, and then you eventually we're going to have a sine squared. And hey, we introduced a sine squared when we make this substitution. So hey, we're on our way to the answer because we've got a sine squared now. And so this is a compound fraction, right? So we want to simplify that compound fraction by multiplying by the denominator. And so let's multiply by cosine squared, because it'll cancel out the cosine squared denominators, right? So we're going to multiply by cosine squared over cosine squared. This one's going to cancel out that denominator. This one's going to cancel out that denominator. And it's also going to multiply the 1. Please don't forget to multiply the 1, right? This is in like parentheses, so it needs to distribute. And so now we're just going to do some algebra and simplify it down. Eventually we'll get sine squared, I'm sure of it. So let me do the intermediate step just in case there's confusion about this. So we have sine squared over cosine squared times cosine squared over 1. And then we have sine squared over cosine squared times cosine squared over 1 plus 1 times cosine squared, right? So I just distributed, and I'm just writing out the details there. These cosines cancel. Those cosines cancel. You end up with just sine squared on the top. Sorry, my pen's falling apart here. And on the bottom, you end up with sine squared plus cosine squared. Now, we know the answer is sine squared, right? And we have a sine squared. And so we're trying to think, like, what do I know about the bottom of this? Well, we know that sine squared plus cosine squared equals 1, right? This is the Pythagorean identity, and it comes up on most trig problems, most trig identity problems, right? So this bottom just changes into the number 1. And so this is just sine squared over 1, which is sine squared. And so we started with the left side. We change things to sines and cosines. We do some algebra. We do another identity. We get down to our answer. But really knowing where the answer is, I really want to remind you that knowing that the answer is sine squared really helps guide me. It makes me feel good about introducing sine squareds up here. It makes me sort of focus on the denominator here because I don't want to mess the top up. That's the answer, right? So it makes me focus on the denominator, and it really just helps guide you to the answer. That's the way I think about it. Thoughts about that at all? Okay, I'm going to write down the next problem that was asked. Just while people are thinking about this one. The next one was asked, that was number 16. And it kind of looks very complicated, but once you do the first step, I think it happens pretty quickly. Okay. Any questions about this one before I flip to the next one here? Doesn't look like it. Okay. So I'm going to flip over to number 16, which was asked. This is what number 16 says. And, you know, a good strategy is always to change everything to sines and cosines, right? That worked on the last problem. We changed tangent into sine over cosine. On this problem, this one's a little bit strange because everything in this problem is already sine and cosine. And so it seems like, what would I really do if I were to try to figure this out? And so to me, when I'm looking at this one, I remember this hidden identity. So we had this quote unquote hidden identity. I can't remember what page it's on, but what I had showed you at one point was if you multiply 1 minus sine times 1 plus sine, and you do some algebra, you end up getting cosine squared. And so that's what this problem is. And I'm realizing that because I've got 1 minus sine here, and then the answer over here is cosine squared. So if I took this and multiplied it by 1 plus sine, I'd get the bottom to be correct. And then I'm pretty sure that if I simplified the top after multiplying by 1 plus sign, I think it would end up being this. And so that's the thing we're going to want to use on this. I think we're going to want to start with the left-hand side, which actually looks less complicated, right? But I'm remembering this hidden identity, and I'm going to multiply by 1 plus sign to make this happen. Right? And so you're welcome to put the hidden identities on your sheet. I don't think I really I usually don't put these on tests, but you're welcome to put it on your sheet for sure. Right? Because look, now on the bottom, when we multiply these two things, this identity is going to give us what we want. We're going to get cosine squared. I'm not going to show you the work for that, but you can double check the notes to see why that's true. I did show you in the notes. And then on the right, on the top, we would distribute, right? We'd do like this and that, and then we would do this and that, and so we'd end up with 3 plus 3 sine x plus sine x plus sine squared. Right, that's what you get after you distribute. And hey, when you add 3 sine plus sine, you get 4 sine. And so we get right down to the answer on that one. So it really hinged on knowing that hidden identity, though. That's what made that one tricky. But you see, like if you knew the hidden identity, it just happened like really, really quickly. All right, I'm going to pause for a second. I did see that there was another question, and I will start pulling up that question, but I want to see if there are other trig identity questions first. I'll also mention that I do have, excuse me, I have another class at 12:30, so I'm happy to keep talking for a while, but I do have to go around 12:30 or a little before, so I can just get a few things ready for that class. I saw one of those students popped in here a second ago, actually. All right, I'm going to stop talking, open up that other homework problem. Let me know if you have questions about this identity one. So Ramon, there's a bunch of log problems. Can you be more? Which homework set are you talking about? Log problem number 4. Log equations, log properties, graphs of logs.
Can you hear me?
Yes.
So this problem is from log property problem number 4.
Log properties, okay. Gotcha. Yep. So this one is log properties number 4. And it wants you to simplify a log into a single log. So simplify into a single log. And you're going to use these properties. So we know that log of two things multiplied, you can split up into them being added. We know that if you have things that are being divided, you can split them up and subtract. And we know that if you have something raised to a power inside a log, you can take the power and bring it outside. And so these are the 3 things that you use on these kind of properties. And here's the thing that's in the problem. So the problem is log base 2 of x plus 5 log base 2 of y minus 3 log base 2 of z. Okay, and I'm actually looking at your specific problem, Ramon, and it looks like you got it correct, but you just didn't enter it correctly. But let me do this one, and then I'll clarify why you didn't get it correct. So notice that on all these problems, if you want to use these problems, there needs to be a number 1 in front of all these things, right? And so in other words, the 5 and the negative or the 3 need to go inside before you can use number 1 and number 2 over here. So the first thing we need to use property 3 to take the 5 and bring it into the exponent and bring the 3 into the exponent. Right, so the first thing we would do here would be to rewrite it like this. right? And now we can use properties 1 and 2 because now we have a 1 in front of all those logs, just like there are in the properties. And so these two things are being added, and so we could multiply them. And these two things are being subtracted, and so we could divide them, right? And so when we do both those things, I'm going to do them both together. I hope that's okay. It would look like this. You multiply the x and the y to the 5th, and then you divide by the 2 cubed. Now, the way that the problem is set up, it tells you, it says the answer is log base 2 of a, and then it wants you just to enter what the a is. So it just wanted you to enter what was inside there, and you tried to enter the whole thing, it looks like.
Oh, okay, that was my mistake.
So I can go ahead and, yeah, that's
the whole thing up.
Yeah, that's not, you did it correctly. That's the most important part. It was a small entering thing, not a big deal.
Okay. Okay, that makes sense.
All right. That takes me to the end of questions that people have asked. What else is on your mind? Other things you guys are thinking about that you would like to review?
I have another question.
Oh,
Exponential equation, problem 5.
one second.
On the workbook.
Yeah, hold on one second.
Okay.
Yep, I have that.
So I did it 2 times and I didn't get it right. Oh, I didn't. I'm not sure if I got it right or I plugged it in wrong.
So it's this problem right here, right?
Yes.
So this is like an extension of the one we just did a second ago. So first thing you need to do is combine these things together, and then you change it into an exponential like we talked about before, right? So these two things are being added, and so you could combine them by multiplying what's inside there. And then you change it to an exponential. And so you do 3 raised to the 5th equals what's inside there, right? So you change to exponential, like using the thing that I talked about earlier, this idea. We have something that looks like this, and so you can change it into something that looks like this, right? You do this raised to that power equals what's inside there. And so this becomes 3 to the 5th equals x times x plus 1. And now this is like just a quadratic equation that we could solve. You distribute the x, right? That goes through there. So 3 to the 5th, I'm just going to leave it as 3 to the 5th. I don't know what that is, but let's leave it. X squared plus x. And now we just get everything to one side, and I would use the quadratic formula, right? So you have like 0 equals x squared plus x minus 3 to the 5th. If you want to figure out what 3 to the 5th is, be my guest, but it really doesn't matter. And then we use the, you sing the song, and we use the quadratic formula. Because 3 to the 5th is a big number. I don't know. It's not worth thinking about factoring it. And so you would do negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. I'm not going to put something on there with something like 3 to the 5th, by the way, but that's how you could do that one. And if you just did that, just leave it right like that. Like don't bother simplifying it or anything like that. That's a great answer.
So let's say in the text, I could just leave it as a quadratic formula.
Yep, yeah, you could leave it
I
right
don't
like
gotta
that.
break it down.
But again, I'm not going to put one on there that's got something weird like 3 to the 5ths.
Oh, okay, sounds good.
Anything else this morning? Speak now or forever hold your peace.
Lester,
Yes?
can you go over linear 3, problem 3? Just to refresh my mind.
Linear 3, problem 3.
Because I know you were over last week with it, but I still have
Sure.
still gotta see it again.
So what do you tell me what to do here. We've done this one, I think, 3 times already.
Yeah, so
Y
we find
equals
slope.
-5x. What's the slope of this line?
You hear me?
Yep, what's the slope?
And it must be.
What's the slope of the line -5x?
Shoot.
Okay, this is the slope. The slope is -5. For a parallel slope, use the same slope. So a parallel slope would also be -5. If you want a perpendicular slope, you make it into a fraction and you multiply it by -1. So I took -5 and I made it into a fraction, and I took -5 and I multiplied it by -1. And so that would make it positive 1/5. I mean, if that's something that's confusing, you should definitely just write it on your sheet, right? For parallel, use the same slope. For perpendicular, make into a fraction and multiply by -1.
Does it always -1?
You make it into a fraction and you multiply it by -1. Yep, every time.
Oh,
So for example, if you had the slope, let's say the slope was 2/5, perpendicular would be flip the fraction and multiply by -1.
how would I write into equation?
Can you be more specific?
Um, um, if you're asking me to put into the parallel slope equation.
Well, you need some point or something to use,
Oh, okay.
right? You would need to use that slope and then you write the equation of a line using that slope. Anything else on your mind today? Starting to get some emails flooding in for my next class here, so I'd like to have a little bit of time to print those out and get them ready. So if there's any other questions, I'm going to go ahead and sign off here. Please just, take advantage of the note sheet. If you need to write something on there, just be writing it on there as you go. Don't, it's already too late. In my opinion, you should have your note sheet, ready, and you should be studying tonight. If you haven't been working on your note sheet, you should be just writing stuff on it constantly as you go now. Write small, just have as much stuff on there as you can. Examples, whatever else you need. Just for example, Ramon, if you wanted to know how to take an equation with a parallel slope and write the equation to line, there's a bunch of examples in the notes, and I would just write one of those examples in your notes if you wanted to have that with you. Okay, I'm going to send out email invites tomorrow morning again, as I mentioned, to specific Google Meet chats. Feel free to send some more questions throughout the day. I'll do my best to answer them. I'm busy today, but I should be able to get back to questions. So I'm around. Please let me know if you want to meet or if you have any questions. You guys can do this. Let's finish strong. You got this. Thank you, guys.
All right, thank you.